Assalamu alaikum, Shabab. Welcome to our lab number 8. Lab number 8 is about AVL trees. And as usual, the objective is to learn how to implement and also how to use, in this case, AVL trees. So as examples, we are given full implementation of the AVL tree as a generic class. It has inside it the AVL node. In fact, we discuss most of this in the lectures. However, here we're going to briefly look at the complete class, explain any other method that need further explanation before we look at the tasks. Okay, so in addition to the AVL tree, we are also given the test integer AVL. There's also another class called word, which we will explain. So all of this, as usual, you get them from the Blackboard. Just go to Blackboard, download lab number 8. It's going to be a zip file. And when you unzip it, you will have the files that you need. Yeah, so let me just try to go to that folder. Yeah, this is the lab 8 folder. So when you unzip, you will actually end up with 2 folders. File IO examples, which I believe I already explained. This is the project that contains the example about file IO that we discussed already. And then you will see the lab 8 folder. So this is the project about lab 8. So you don't open, as I said last time, you don't open the lab 8 source files from here. Rather, you go to NetBeans and browse to locate the project and open it. Okay. There's also usually the lab document. This is the one we are going to go through for necessary explanation and instructions on what to do. All right. The other files are about text file IO, which I already explained in the lecture. Okay, so let's go back to the document. Now, before we look at the code, which we shall do in a moment, actually let's do that first. So let's go through the NetBeans to look at these files. Okay, so this is the project for lab 8. As I mentioned, it has AVL tree, it has AVL tree printer, so very similar to BST printer. The idea is to print the AVL tree as we do insertion or deletion in a form that looks like a tree, so that you can see what is actually going on, including all the rotations involved in this case. Okay. Let's start with the AVL tree class. As you remember, it has to have T to be comparable, just like the BST. So there is nothing new here. It's actually essentially the same as BST tree, except for the changes we had to make to the insert and delete method. And as we recall, the insert and delete method requires rotations. So the rotation methods are also introduced, and any other necessary method that is needed just to achieve a balanced tree. Okay, so all the methods that we discussed about BST are here, except with the modification to insert and delete, and the additional methods that are needed to make the insert and delete method work. Okay, so nothing new other than that. Of course, we have changed the name of the class to AVL tree. So instead of seeing a BST node, you will see AVL node and so on. But other than that, most of the things are the same. So nothing to explain about the constructors or the get root method, the same as in BST. we already explained the changes made to the height method. Now we don't have to compute it because the height is being saved inside the node. So just say p.height to get the height. Okay, this is the insert method as we discussed in the lecture. Most of it is the same except for the part that is doing the rotations. So if you insert on the left, you have to do one of these two rotations, either rotate right or rotate left right. And similarly, if you insert on the right, you have to do you have to do one of the two rotations, either rotate left or rotate right left. All right. The delete method is also explained in the lecture. The step number 1 is exactly as in BST, deletion by copying method. And then after that, you have to update your height and then do the balancing. So all this is explained in the lecture, nothing to add. The get min node method is the same as in BST. We needed this in order to find the successor to help us do the deletion by copying. Okay, this is probably a new method which we didn't have to have in the BST. How do we get the balance factor of a node P? Well, as the definition says, balance factor of a node is height of its right subtree minus the height of its left subtree. Except, of course, if the tree is empty, in which case you just return 0. So this is straightforward. Get maximum node is not needed in this code. If you wish, you can delete it. Because the idea is, if you are doing deletion by copying, you have two options. Either you find the successor, which is the minimum from the right, or you find the predecessor. Okay, so the predecessor is the maximum from the left. Okay, so you go to the left and you keep going to the right until you find the one that is rightmost, that is the biggest from the left. So that's going to be the predecessor. But I don't think we use this method in this class. Okay, we already explained about the rotation method. Rotate right, you already saw that. Rotate left, you already saw that. What probably you didn't see, because I forgot to put it in the PowerPoint slides, are the double rotations. But as you can see here, the double rotations are just calling the basic rotations. So for example, to do a left-right rotation on a node P, we first do the left rotation on its left child. So you see here, rotate left, we do the left rotation on the left child, yeah, so rotate left, P dot left. Okay, and update P dot left to be the result. Then now rotate the node P itself to the right. And similarly for the double right-left rotation. The right rotation is on the right child. So rotate right, what? P dot right. Save your result as P dot right, and then now do the left rotation on the P itself. So these were the two methods that we didn't explain in the lecture. They are just calling the two basic rotations. Only that the first rotation is normally on the child, and then the second rotation on the node itself. The iterator, there is nothing to explain. It's exactly as in BST. So other than changing the name, nothing has changed. So there is nothing to explain here. We saw the AVL node class with the addition of the height variable. So that has already been explained. The rest of the methods, I believe, are the same as in BST. Clear is empty, visit, search, no change at all. Remember, we were trying to make the searching to be efficient, That is why we had to improve on the way we do insertion and deletion. So the tree is always balanced. So this searching is always going to give us the best possible result in terms of the running time. Okay, no change in the is in tree, and no change in the traversal method, exactly as in BST. The only change is the name of the node. Now it's not BST node, it is AVL node, and so on. So all the traversal methods are exactly as we discussed in the BST. So this is the AVL tree class. Right. Now, in addition to the AVL tree class, we are given a test class or a main class to test the AVL tree as usual. All right, so it has exactly the same options as we saw in BST: insert an element, search for an element, delete for an element, and then do one of the traversals. And there's a last option here to clear the tree, just to test the clear method. Okay, I think I removed the method that was testing the iterator, because that is not the point here. We already saw that with the BST there is no difference. All right, so handling each of these options is basically just calling the appropriate method. So for insertion, we have to ask the user to enter an element, then we call the insert method to do the insertion. Insert what the user has entered on the keyboard. However, here, like in BST, after the tree has been updated with the new value, we want to display it graphically to the user. So this is the purpose of AVL tree printer. So you just create the object of that class, pass into it your tree as argument, and then call the .print method. So it is used exactly like BST printer. And as I mentioned in the BST lab, we are not required to know how this class is coded, just how to use it. Of course, if you want to know how it is coded, it is there for you. You can go and look at the code. But learning how the code works is not relevant to us. Okay. So we're going to do it similarly when we do a deletion. So after each insertion or deletion, we're going to display the tree graphically. Okay, but the next option is about searching. So this is similar to BST. Just call the search method after getting the target from the user. Okay, and save your result. The result of the search is saved as an integer object. And now check if that object is not null, we print the result. Otherwise, we print an error message. So exactly as in BST. For deletion, however, as I just mentioned, after you read the input and call the delete method, we need to display the resulting tree graphically. So you will call a method of the AVL tree printer object to do that. Right, the rest are as before, just the traversal, breadth first, pre-order, in order, post order, and clear. So that's about the class. Now, before we run it, let's go back to the lab document. The first task here is actually manual. Like we did with BST, it is very important for you to know how to do AVL insertion as well as deletion. Well, these tasks are basically about insertion. So it says for each of the following, insert the given sequence of numbers manually into an initially empty AVL tree. Show all the rotations involved by drawing a separate tree after each rotation. Note, for double rotations, you must show the result of each. So you are given 3 examples. to help you practice how to do AVL insertion. In fact, if you notice, this first example is exactly the example I solved in the lecture. The second example in the lecture that we solved in full, constructing from the scratch, is exactly this one. Okay, but these are new. So try to see if you can construct AVL trees using these sequences. And then it says, after you've done that, run the test integer AVL to verify your solution. Okay, so I'm going to run the program now and see how these elements will be used to construct an AVL tree. You will see that it will be exactly as we discussed in the lecture. Now I have already started running the program. Okay, so let us run the test integer AVL to see how it works. Actually, I have already started running it. So let us go. We're going to use the first example there in the document to insert the element and see how our insert method do the rotation. The first value is 5, so we choose insert, and the value is 5. Okay, being a leaf node, there is no problem. Next is 15. 15 obviously will go to the right of 5, and so far the tree is balanced. Now the next value to insert is 18. Obviously 18 will go to the right, so let us see what our program will do if we insert 18. Right, so actually you can see when you insert 18, it went to the right, and the tree becomes unbalanced. Actually 5 becomes unbalanced because it has 2 elements on its left subtree, or it has height of 2 in the left subtree and 0 on the right. Okay, so the problem is there for right, and the solution is single left rotation. Now notice what is here in the output. In addition to the tree, there is a very important message here actually, which is telling us what was done to the previous tree after the insertion of 18 to achieve this new tree. Rotate left about node number 5. So you may be wondering, where does this statement comes from? This statement actually comes from the rotate left method. If you notice, there are print line statements in each of the rotation methods. So the rotate right, the first line says here, rotate right about node p dot key. Similarly, rotate left will say rotate left about node p dot key. Okay, rotate left right says double rotation is required, and when it calls rotate left will print its own message, and when it calls print rotate right, it will also print its own message, which node was rotated and so on. Now these are just explanatory notes. I expect you, after running our example, to actually comment this print line statement. They are not supposed to be part of the method. They are just to help you in case you are still learning how to do the rotations. After each operation, the rotation method will tell you what is going on. So certainly before you do task 2, I expected you to come inside this rotation method to comment the print line methods. They are not part of the rotation operation. They are meant to be just a guide to you to know what is going on when you are running the program, at least for the first time. Okay, so let's go back to our sample run. Now the next value after 18 is 4. So 4 obviously is less than 15, less than 5, so it's going to go to the left of 5, and there is nothing to do because the tree will still remain balanced. Okay, next is 3. So option 1, 3 is going to go to the left of 4 still. So at that point 5 becomes not balanced. It's a left, so we have to do a right rotation. Okay, let's see that. Yes, you can see what happens. And it is telling you again, rotate right about node 5. Yeah, so this is telling you what happened to the previous tree after inserting 3. Node number 5 was rotated to the right. Next value is 1. Now 1 will be to the left of 3, and in that case the node that is not balanced will be actually 15, because 4 is still fine. It has 1, 2 on the left and 1 on the right. Okay, so let's do that and see. Insert 1. Yes, so this is what we got after rotating 15 to the right. Okay, see, if you rotate 15 to the right, it will go down and 4 become the root, and 15 will be the new right subtree of 4. What happened to the current right subtree of 4? It will be the left subtree of 15. As you can see here, 5 is to the left of 15. Yeah. Next element to insert is 9. 9 will go right of 4, left of 15, but right of 5. So insert 9. And it seems there is no issue after that insertion. All nodes are still balanced. But now if we insert 7, which is the next element, you will see that 5 will not be balanced. It has a right problem, so it's going to be rotated to the left. Okay, so insert 7, and you can see the result. And the explanation is, this is actually very interesting, because after we insert 7 actually went to the left of 9, not to the right. I'm sorry. So the problem therefore is not right, the problem was right, left. Therefore we need to do a right, left double rotation. Okay, the right rotation will be on 9, and then the left rotation on 5. So this is exactly what these statements are telling us what has been done. It says double right, left rotation required. Rotate right about node 9, then rotate left about node 5. Okay, and this is the result that you're going to get. So if you are doing this manually, this teaches you what to do. And this is the importance of those print line statements inside the rotation method. But as I said, once you learn how to do it, just comment those methods. They are not needed as part of the rotation operation. The final value to insert is 12. 12 will go to the right of 4, left of 15, right of 7, right of 9. So at that point, I think 15 will be unbalanced, and the problem will be left, right. Okay, let's insert 12. Yes, and this is what you get after that rotation. This is exactly what we saw in the lecture slides. So this is basically teaching you how to do the insertion. You can go ahead and test all the other methods like searching and deletion and so on. For example, suppose we delete a 4. Okay, what will happen? It's going to be deletion by copying using successor. So the successor of 4 is 5. So 5 will be copied here, and 4 will be deleted, and then the 5 itself will be deleted. The question is, after that, is there any rotation needed? I don't think so in this case. The tree will still remain balanced. Let's try that. Delete 4. So option 3. Okay, delete 4. Yeah, you can see 5 has gone up to replace the deleted node, and this is the tree that you're going to get. However, now if you delete 7, then there's going to be a problem, because 9 will not be balanced. And remember, if you delete a node, you have to take care of not only its immediate parent, but all the ancestors until you reach the root. So we will solve the problem of 9. If we solve the problem, fine. Otherwise, 5 also has to be rotated. Okay, let's attempt that. Suppose we delete 7. Option number 2. Sorry, option 3. We want to delete 7. And you can see what has happened. 5 is not affected. We only need to rotate 9 to the right, to the left, because it will have 2 on the right, and nothing on the left. So a single left rotation will solve the problem. So 15 will go up to be the root. 9 will be its new left child. The present left child will be to the right of 9. And this is what you have. 12 is now to the right of 9. Okay, so basically this is the idea. I don't think we have to go through the testing of the traversal methods. They are exactly as in the BST, the same thing with searching. The main changes are insertion and deletion. Now they are ensuring that the tree is always balanced by making the necessary rotations after each insertion, so that our tree is always balanced. This is the point of the example. Now let's go back to our lab document and see the remaining tasks. Okay, task number 2A. It says the text file about JUC.text, which we already saw in our explanation about text file IO. It contains basic information about JUC, and actually it is obtained from the website. We are asked to write a program called print words that uses AVL tree to print the words in the file, but here is the catch. The words should be sorted alphabetically. The words should be sorted alphabetically. Now, if you recall, we already have a program in the text file IO example that will read that same file and print them word by word. Okay, so it opened the file using and create a scanner object using that, update the delimiter, and it will now read the words one by one and print. Okay, if you run it, you will see the output just like before. We have to actually run file because we have more than one main class. So read from file 2. If you run it, just to remind you, this is the output. The words are printed one by one. But notice that they are printed as they are encountered. They are not sorted. Science in Business Administration, Bachelor of Science in Human Resource Management, and so on. So the words are printed according to the way they are encountered in that file. So what our task here is saying, print the same words, but this time they should be sorted alphabetically. Okay, so here is the hint. It's very easy task actually, just one line you need to add to that particular example to make it to print the words alphabetically. It says you need to read the content of the file word by word. However, for each word encountered, you need to insert it into a tree. Don't just print it directly, insert it into a tree. So you're going to create an AVL tree of strings, and then when you read a word, insert it into that tree. After you finish reading all the words and inserting them into the tree, now print the tree using in-order traversal. Remember, in-order traversal will print the content of a tree in increasing order. In this case, since the content are strings, they are going to be printed alphabetically. So really all you have to do is here in the read from file. When you read from the file, when you say reader.next, don't say system.out. Rather, you should say tree.insert. So you will have created a tree somewhere above here, a tree of string. So after you read a word, insert it in the tree. Each time you read a word, insert it in the tree. After the loop, now print your tree using the in-order traversal. How do we do that? It's already here. Tree.inOrder. This is how to print the elements in order. So just call the in-order method on your tree, and you will see that the words in that tree are printed alphabetically. Now you can see the reason why we had to learn about text file I/O, because if you are to enter all the words in that file one by one into a tree, it's going to take you ages. Okay, so we now have the knowledge of how to actually read the content of the file and insert them into our AVL tree. And then now when you print the tree, you see that the words are sorted. Good, so that is the first task, which is very trivial, just about 3 lines you need to add to the already given example to achieve that. Okay. B. It says your program in A will have automatically discarded all duplicate words in the text file. Because what? As we know, BST and AVL trees, they do not allow duplicate elements. Okay? So if we encountered a word, for example, like Bachelor of Science in Computer Science, Bachelor of Science in MIS, and so on. There are many repeated words in that file. Our program in A will have stored only one occurrence of Bachelor in our tree. Now we want to improve on that. It says write a program called print word counts that will print each word in the input file along with its count. So we want to know how many times does each character, each word occur in that file. Okay. Here is a hint about how to do this. It says for each word encountered, use it to create a word object. Okay. So maybe at this point we need to look at the word class. Let's go to the word class. I gave you a small class called word. Let's go and see what is inside. So the word class has 2 variables. A word, which is of type string, and a count, which is of type integer. Okay, so associating each word with its count. I deliberately made it public here to make your code in that task easy. Okay, so the constructor of the word class, it will receive a word as a string and just initialize this instance variable with that, but also initialize count to 1. So each time you create a word, automatically it has a count of 1. Okay. Now, but you can update this count because the variable is public. So from any class, you can say count plus plus or word.count plus plus to increment the count. Okay, good. So that's what we will be doing. I will explain this in the hint there in the document. But let's read the rest of the class. It has three methods: equals, okay, which will compare based on the word, not the count. So two word objects are equal if they have the same word. Also, it is comparable. This is very important. Otherwise, we cannot insert it into BST or AVL tree. So if it is comparable, how do we implement the compare to? Well, the compare to is implemented based on the word. Okay, now luckily for us, string, as we learned in the lecture, implements comparable. So this, our compare to method, will simply call the compare to of the string class, comparing the current word against the one that is received as argument, and return the result. Okay, so it's basically saying to compare two of the two word objects is going to be done based on the string itself, not the count. Okay, the final method here is the toString, which will print a word and its count. So now with this class, we can go and explain what you are supposed to do here, because we want to print each word with its count. So what you do here, you don't create a tree of string, AVL tree of string like we did in task A. No, you're going to create an AVL tree of word. Okay? So when you read a word, don't insert it directly into a tree, into the AVL tree, because it will not go. The tree is not a tree of a string. It is a string of words. So you're going to create a word object. Okay? You can call that your object target. Okay? So word target equal to new word. Okay? The next word you're going to read from your file. Okay, so once you have this target, next thing is to search for it in your tree. Did you encounter it before or not? If the result of your search is true, the word already exists in the tree, then if you try to insert it, it is simply going to be discarded. So what you do, if it is found, increment its count. Increment the count of the one in the tree. So you're going to increment the count of result, which you use to receive the result of the search, not the count of target. Target is not yet in the tree. It is only used for comparison. Okay, so do a search, save your result of search in a variable called result. Now you check. If result is null, then it means the word doesn't exist, so you insert it. But if it is not null, then you just need to increment its count. Okay, so it says if found, increment the count, else insert the target in the tree. Okay, so this ensures that we don't just discard a new additional word that we find, rather we increment their count. So by the time you finish reading all the words, they will have all their counts along with them inside your tree. So all you have to do now is to print your tree again in order. This is the idea. Just to give you a sample of what we expect, this is the expected output, except for the last part here. So for example, here it is saying A was found one time, about was one time, but let us see let's see degrees was also encountered one time. I want to see the word bachelor. I hope I have it here. Yeah, bachelor was encountered 11 times. Okay, so this is what your output should be, not with the last part. This is going to be explained in task number C. Okay, but for B, I should just have for each word, how many times was it found? For each word, how many times? Can was found 2 times. City was found 3 times. I guess with Jebel Industrial City, and so on. All right, and you can see that they are printed alphabetically. So that is about task number B. Okay, what is task number C? Task number C says, save your print word counts as print word lines. So you're going to refactor your program in B and save it as print word lines. And update it to print not only the count of each word, but also the line numbers where the word was found. Okay, so that is the sample output we are seeing here. In addition to the count, we are now being told which lines inside that file did we find the word bachelor. So this one is saying it was found in line 7, line 8, line 9, line 10, 11, 12, 13, 14, 15, 16, and 17. All right. If you go and check that file, it will have all these words inside. Okay, so this is the last task. And here is the hint about how to go about it. We need to update our word class to have one more variable to record the line numbers. So it is saying, first of all, save the word class as word info class and update it as follows. 1. Add a variable called lines of type linked list. So we're going to store the line numbers as a linked list. Okay, to store the line numbers as each word is encountered. Second, update the constructor of your word info class to receive not only the string this time, the string of the word, but also the initial line number. So when you encounter a word first time, of course, it has a line number. So your constructor will add that line number to your linked list, the additional variable linked list. Then, of course, you need to update the toString method to print not only the word and the count, but also the linked list, so that we can see the line numbers. And finally, you're going to update the compare to method to ignore the case between words being compared. Actually, you're going to, right now, if you run your example, you will not get the same output as I have here in the Word document. You will see that the capital letters appear first before small letters. Now, we don't want that. We want the words to be printed alphabetically irrespective of their case. Okay, so here you see I have a mixing of accounting, then achieve, then administration. Okay, how do you achieve this? It's very simple. Just go to your word info class. In the way you implement compare to, change this calling of the compare to of the word of the string class. Call instead compare to ignore case. You see the string class has not only compare to. Let me show you. If you say what, you will see the list of methods. Compare to ignore case. Yeah, you see there are two compare to. There's compare to and there is compare to ignore case. This is the one you should use. If you do that, then your compare to method will compare two words irrespective of their case. Yeah, this is the idea. So that's what I'm asking you to do as a hint to make sure the words are printed alphabetically irrespective of the case. So those are the changes you need to make to the word class. So you're going to use this to create your AVL tree. And now you need to update your program as follows. Okay, so create an AVL tree of your word info objects. And secondly, in the previous two examples, A and B, two tasks rather, task A and B, you are reading the words word by word. Now, if you read the words word by word, you will not be able to know which line number did you encounter a word. So I am suggesting here, do not read the file word by word. Instead, read the file line by line. In that way, you know what line number are you reading. So read the word line by line. Of course, when you read a whole line, you now have to process the line because the line contains many words. Okay, but they all have the same line number. So I am suggesting for you to use a method of a string called split. This split method, if you give it a string, it will split it for you into individual words. Okay, it's going to give you an array of string, okay, containing the individual words. So after you read a line, call the split method to convert it into an array of string. Then now you need another loop to go through the content of your string. Each word in the string, in the array, you will use it to create a word info object. So it will have the word and the same line number as the rest. Yeah, so those are the two things you need. And you do exactly as in C. You're going to try and see if this word exists in the AVL tree. If it exists, you will update not only the count this time, but also the line number, because if you are encountering, again, maybe you encountered it before in another line, so you have to add the new line number. In summary, this is what you have to do to achieve task C. I should emphasize the split. By default, if you don't give anything, it will split the word based on space, white space. But we want to split the words ignoring punctuation characters, remember? So you can use the same regular expression that we use to discuss the what is it called, the delimiter, the one that you use to update the delimiter. Use delimiter method. You remember when you create a scanner object, you updated the use delimiter method to ignore punctuation characters. So you're going to use the same expression to your split, because when you read a line, that line may have punctuation characters, and we're going to split the words in that line using the split method. So we can tell the split method, use delimiters to be not only spaces, but also punctuation characters, so that the array of string that you're going to get will have no punctuation character, just the word themselves. So once you have this word, now you need another loop to process them. For each one, you're going to create a word info object, and then try to see if it is in the tree. You need to just update the count and the line number. If it doesn't exist, insert it, just like before. So after you finish all that, print your tree in order, and you will have this exact output. This is basically what this lab is about. So just processing the text inside the about.juc.text using AVL tree. This is the end of my explanation about the lab. You have, like we did last week, you have until midnight on Saturday to submit it, so that I shall have it by early morning of Sunday. Thank you very much and good luck. Assalamu alaikum.